It's my pleasure to continue the lectures on random matrix theory. Today's lecture, so maybe might be that there are two lectures today, but the first lecture of today is lecture 2 of the random matrix course. That is on the mathematical physics aspects of random matrix theory. The day before yesterday, we went through a tour de horizon. So we looked at different aspects of random matrices, phenomenological ones and some basic mathematical ones and so on. But we did not really explore the very deep and very rich mathematical structures. But random matrix theory is a field of mathematical physics. It has relations, of course, I mean, this is how it originated, to data analysis in a very explicit way, and it's used for that very, very often. But the mathematics connections are, I would say, equally strong. I mean, there are now people doing random matrix theory in the math department or in the statistics department who have no connection whatsoever anymore to data and to experiments. And of course, I mean, this is people do what they like, what they believe is important. This is not quite my approach because I'm a physicist, but still the mathematical physics aspects are also very, very important for physicists working on random matrix theory. Okay, outline of today's lecture number 2. I want to start with discussing the transitions. I spoke about them already a little bit the day before yesterday, and I want to use that as the entrance door to harmonic analysis. Harmonic analysis is a mathematical expression. Harmonic means that it first appeared in the context of acoustics, but what it actually is Fourier transforms, and very often on complicated spaces, curved spaces, and multidimensional spaces and such things. But it's essentially what we as physicists would call Fourier transformed on complicated spaces. And in that case, functions appear which generalize the Bessel functions. So Bessel functions, that is, I would say, the first field where harmonic analysis was identified as with that name. There is a second connection, very popular in mathematics, that are exactly solvable systems. And we will see that this connection is very, very close. Now, the second part of this second lecture is about supersymmetry. First of all, into supersymmetry as a new mathematical concept. So I will first speak on supermathematics and then show how it enters as supersymmetry to random matrices, and I will also make the connection to disordered systems because that is actually where it came from originally. Okay. Yep, I have here to use this. Yep. But before we do that, I want to repeat some of the salient features just to set the tone, which I have already mentioned day before yesterday. So we are talking throughout the talk about 3 matrix spaces. These are symmetric spaces in the language of mathematics. So if we have no invariance under time reversal, we talk about Hermitian matrices labeled beta equal 2 because every entry of such a matrix has a real and imaginary part. If we have invariance under time reversal, we can have 2 different cases: integer spin or half odd spin with rotation symmetry. In that case, H is real symmetric, so just based on the real number. So beta, the Dyson index, is 1. If we have half odd integer spin without rotation symmetry, then we have Cramer's degeneracies, which is an observation made by Cramer's once. And then the matrices are Hermitian self-dual. That is a case which I will not touch so much, but actually most of the formulas which I present you would also apply with only very few modifications to this case, beta equal 4. Now, this classification is actually due to Wigner and von Neumann and almost 100 years ago. In mathematics, there was a pioneering work. I mean, it's amazing, by Guhr in the 50s. And it went almost unnoticed in the West. but the Russian mathematicians noticed it. So the people around Gerd Fund, Naimark, Zetlin, and so on. So it is actually it is really enormous. I mean, when you read it, it's amazing because some parts of it read as if it was a very modern paper of, you know, with state-of-the-art discussions of today's questions on harmonic analysis and on symmetric spaces. So just for mathematicians, so let me reiterate this labeling here. So the real symmetric matrices are, from a mathematics point of view, they span the space of UN divided by ON. The Hermitian ones, UN divided by 1. Put differently, unitary matrices and Hermitian matrices are almost the same. The only difference is, from a practical point of view, that the eigenvalues of Hermitian matrices are real numbers. The eigenvalues of unitary matrices are phases, E2, I, phi something. And U2n divided by SP2n, these are the Hermitian self-dual matrices based on quaternion spaces. Yeah, and Dyson's threefold way consists of equipping these spaces with probability densities and a flat integration measure, defining the Gaussian orthogonal, unitary, and symplectic matrix. The point is here, and that will be very important soon, that these are invariant ensembles, which means they only depend on traces, or more generally on traces and determinants. So they only depend on the eigenvalues of the matrices which are which enter here this expression, so on the eigenvalues of the random matrices. But this suggests very much to introduce the eigenvalues and the angle as new variables. So if we diagonalize each of these matrices in the 3 different symmetric spaces with matrices from ON, UN, or USP2n, and with the eigenvalues, which are real numbers, then we have to double them for beta equal 4 because of Cramer's degeneracy. We end up with this expression. And here you see this Gaussian function hasn't changed. I just write it now in terms of the eigenvalues. But this flat integration measure, that became this here. So consisting of the harm measure of the group in question. Harm measure means we treat all parameters on the group manifold on equal footing. I'll tell you in a minute a bit more about that. And this is Jacobian aperion, and this Jacobian is a Vandermonde determinant lifted to some power beta, beta being the Dyson index, and this is difference of all energies. And I want to reiterate again that this is the essence of random matrix theory. Whenever 2 eigenvalues degenerate, the right-hand side of this equation is 0. So the probability of having degeneracies is very strongly suppressed. In the 90s, Altland and Zirnbauer extended that to the tenfold way. And I don't know if Alexander will speak about that next week, but I won't. I just mentioned the day before yesterday the connection to the chirality. That is one extension, but there are also other extensions related to the Andreev scattering. Okay. But we stay with a threefold way. Yeah, and this is a mathematics definition of the correlation function. It is a PDF of finding one level in each of the intervals, EP to EP plus DEP, P running from 1 to K, regardless of label. Which means we just integrate out of this joint PDF of all n eigenvalues, we integrate out n minus K. And amazingly, this can be done in closed form. I don't go through the calculation here. Even that is a mathematical physics part now. I don't go through the calculation because this is really textbook stuff now for decades. So if you're interested in this aspects, I recommend that you go through. I mean, there are several editions of Meta's book, and in which that is presented in much detail. No? But I just want to tell you that the result is very nice. In the unitary case, beta equal 2, it is a determinant of such a kernel consisting of oscillator wave functions. And in the beta equal 1 and beta equal 4 cases, so in the cases where time reversal invariance holds, then we have Pfaffian determinants. Actually, Dyson calls them quaternion determinants. So the definition is then slightly different, but essentially it's the same. Yeah. Once more, we have to do all that on the unfolded scale, on the local scale of mean level spacing, which means the density after the unfolded scale, now referred to as x1, not r1, has to be 1. And the correlation functions, now xk instead of rk, become fairly simple determinants for beta equal 2 of this form here, of the so-called sine kernel. And more complicated expressions. Actually, Barbara showed them the day before yesterday for beta equal 1 and beta equal 4. So that was a short reminder. Now let's go to the transition ensembles and how that leads to harmonic analysis. With transition ensembles, I just want to account for the fact that in reality, we very often have combinations of the symmetries that we have been discussing. Which means we have a matrix in one of the three ensembles, here indicated H upper index beta, and something else. So this H0 could be a regular matrix. It could be a matrix also taken from the Gaussian ensembles, but from a different Gaussian ensemble. So for example, if beta is equal to, and H naught is H stands here then for the matrices taken from beta equal 1 or beta equal 4, then we would have a transition as a function of this parameter alpha from a system preserving time reversal invariance to a system breaking time reversal invariance, and gradually as a function of alpha. So one condition, of course, for these transition ensembles is that the symmetric space in which this H upper index beta is defined includes that of H0, which means if H upper index beta is the symmetric space of the Hermitian matrices, so if beta equals 2, then H0 could be a diagonal regular matrix, it could be a real symmetric matrix, it could be a quaternion self-dual matrix, no problem. But if H beta is taken, say, from the Gaussian orthogonal ensemble, so only real symmetric matrices, H naught should not be taken from, say, the unitary ensemble. So it should not be taken from the ensemble of Hermitian matrices. So that is a convention we have to do here, but you see, this is not a restriction whatsoever because we can just swap the meaning of H0 and H beta and then cover every case. So obviously, the eigenvalues of H viewed as a function of alpha are highly non-trivial. Obviously so. I mean, even if we know the eigenvalues of H upper index beta and H upper index 0, they don't give us directly the eigenvalues of H of alpha. No way. Okay, so what can we do about it? Actually, we are not really interested in these eigenvalues. We are only interested, and that's a big difference, in the joint PDF of these eigenvalues. So we agreed upon that the H beta space is the most general one, including the space of H0. So let's assign a Gaussian probability density in the usual form, and here I include the normalization factor to this H upper index beta. You see, V squared is a variance appearing here, and that is a normalized Gaussian probability density. So if I take the limit V to 0, so the standard deviation V, or the variance V squared to 0, I get a delta function. I get the delta function of the matrix elements of H upper index beta. And now comes the trick. Now I say, okay, I just solved this upper equation here for H upper index beta. So I replace as integration variables the H upper index beta by the entries of H of alpha. So I replace this H of beta by H of alpha minus H upper index 0 divided by alpha. And use the H equal to H of alpha as the integration variables. If I do that, and if I also take care, because it's a PDF of the Jacobian of this change of variables, I see that I get a new Gaussian probability density, which is also normalized, which is a function of H minus H upper index 0, with a new standard deviation, alpha times v. So this equation here with v replaced by alpha times v, and here in the argument I have trace of h minus h0 in brackets squared. Aha! That means if I take alpha to 0, I get again a delta function. And now I get the delta function h minus h0. Let's see what that means here. Aha! H equals h0 means makes sense, alpha is 0. Aha. So that is fully consistent. So we have on a statistical level exactly a description of this situation here. So what do we have to do next? Well, we need the information on the joint PDF of the eigenvalues of this h. So we have to integrate out, and now it's getting complicated, the diagonalizing angles of h upper index beta as well as the diagonalizing angles of h upper index 0. Let's diagonalize them. So h is diagonalized in this way, E being the diagonal matrix of its eigenvalues, and h0 is diagonalized that way with the matrix V and the eigenvalues E0 again ordered in diagonal matrix. Now you might say, well, you know, sometimes I would like to take an h0 which is already diagonal. Okay, then you do it. Then you replace V with a unit matrix. Huh? Then you say, okay, I never want to average over the V. Okay, fine. You will actually see it won't make a difference. Yeah? It might sound like a difference now, but you will see in 2 minutes that it won't make a difference. So this choice that the h0 is diagonal and fixed is included. I tell you now how. Okay, let's assume that we do this integration now. So we integrate this new probability density over these two diagonal matrices of U and V. U and V. Now, this is dependent on e to the minus trace h minus h naught squared. I multiply it out, so I have a trace h squared. Well, that's an easy one. Trace h squared is equal to trace e squared. That's this term here. I also have a trace h0 squared. That's another easy one, because that is just trace e0 squared. Okay, that's that term. But now comes the difficult term. That is a term, the mixed term, where I have to multiply h and h0. Here I have h and here I have h0. So I just write it down, the product of h and h0, and now you see, whoa, that is a nasty term in which the groups really enter the diagonalizing matrices, and here I have to do a highly non-trivial group integral. So we have to, again, think about these Haar measure. And now I want to explain a bit more precisely what it means. So you want to be the Haar measure in such a way that you can always integrate over the group space and are always certain, sure, that you treat all points on this group space, on the group manifold, on equal footing. But that means the following. This Haar measure has to have the following property, that is a defining property. If I move the group element U by a fixed group element V, or V to the minus 1, would be the same, because if V is in the group, V to the minus 1 is also in the group. This should be fully equivalent to the measure on U itself. So it doesn't make a difference where you start on the group manifold and how you do the summation over the group elements. Of course, you would say now, well, but I would like to multiply the U from the left-hand side with V to the minus 1. That's true. This property you should also have. So that would be the left and right invariant Haar measure. But here we would only need this type of invariance, because you see, if that holds, I can simply absorb the V minus. And you see here also, I can move, due to the invariance of the trace, the U minus 1 to here, and write it as U times V minus 1 in brackets 2 minus 1. And then again, I have only the U. So you see, if I interchange these integrations here of U and V, then I can first absorb the diagonalizing matrix V of H0. I can fully absorb it into the measure of U, and then it's gone. It's just gone. And then the integral over V becomes trivial. It's just the volume of the group that enters. Put differently, this double group integral is fully equivalently mathematically identical to this group integral, to this single group integral. Yeah? This is very important. And now you see it really doesn't make a difference if I choose an H0 which is diagonal or non-diagonal or whatever. Huh? It will always be this integral what we have to do and what we have to worry about. But this is a nasty integral, a really nasty integral. Oh, by the way, if you feel like asking questions, don't hesitate. Yeah? So you are free to also ask questions during my talk or afterwards, just as you like. Huh? So I guess in that, if you have question, I think Barbara will tell me. Okay, now I write down this very integral which we just had, so this here in a standard notation. The standard notation is the following. One uses X and K as diagonal matrices. I tell you in a minute why. And one also introduces, which is really convenient, an imaginary unit here. But this really doesn't make a difference because the integral is only over a compact group. That means this is not something like the Lorentz group or something like that. So it is always only a rotation. It is not something, so it's only about circles or rotation in circles, not about hyperbola. So the matrix is only 1, 1, 1, 1, 1, 1, 1 in all dimensions. It is not minus 1, 1, 1, 1, as in the case of the Lorentz group, which means the elements of U in any type of parameterization are sort of confined, they're finite, so you can always write them in terms of cosines and sines, which means this integral can never diverge. So there is no divergence that can appear whatsoever. So I'm free to insert here an I without changing the analytic properties of this integral in any way. Okay, now I want to tell you how this integral relates to Bessel functions. And it's actually a matrix generalization of Bessel functions. So what is a Bessel function? A Bessel function is you have two vectors, say a vector r and a vector k, so position vector and a wave number, and so there's some angle between them, and now you want to average over the space and over the angle between them. This is what a Bessel function is. And here we want to do the analog of that for matrices. So we start first with a Cartesian matrix plane wave. So in Bessel functions, we have the plane wave e to the I k dot r. And now there's an angle between k and r. So this is something like cosine theta or so. And now we want to average over all angles. And here we want to do the same. So we have a matrix plane wave. So we have eigenvalues, which are the radial coordinates on the symmetric spaces. We have diagonalizing matrices, and we want to average over them. Okay, let's start with a matrix plane wave. Sorry, a properly defined Laplacian over any of these matrix spaces I've been speaking about, acting on this matrix plane wave, reproduces minus trace k squared. This minus comes from the I, which we have here. So it's minus trace k squared times the matrix plane wave again. Okay, so what is this Laplacian? It is really simply the generalization of a gradient squared. So you can define a matrix gradient by just taking the matrix elements of H, replacing them by their derivatives, and now you have to face the problem that there are symmetries. So that's a matrix real symmetric or Hermitian or something like that, which means you have to avoid double counting. So therefore you have to introduce some factors of 1/2. If you do that in a right way, then you get something like this. So it's just a sum over all these derivatives with respect to the matrix elements, and the C and M's are just properly chosen factors of 1/2. So I don't want to write it down in full glory for all cases, beta equal 1, 2, 4. But if you have fun, you can do it. I mean, it's just you properly have to include factors of 1/2. And if you're not sure that you find the right factors of 1/2, you want that this Laplacian really reproduces this matrix plane wave equation. So this is how I would reconstruct this Laplacian. Okay. Now we want to do what we do in the case of vector Bessel function. We want to integrate over the diagonalizing groups. In that case, we assume that A and K are in the same spaces. Now you might say, whoa, but that is different from what we had in the case of transitions. Yeah, it is, but again, you will see it makes no difference in the end, again, due to the invariance of the harm measure. So let's, for the time being, consider this more restrictive case, and then you will see, wow, it actually also includes the case that we just discussed for the transitions. So H and K are in the same symmetric spaces, so they're either real symmetric, Hermitian or Hermitian self-dual, big U1 to 4. So U and V are either from the orthogonal groups, unitary, or the unitary symplectic group. So now here we have again our matrix plane wave, and now let's integrate over the diagonalizing matrix V of K. So not the diagonalizing matrix U of H, you integrate over V of K. Why? Well, because of this here. So this Laplacian also contains degrees of freedom with respect to U. So we cannot just... then we have to think very carefully what we do if we want to integrate the whole equation over U. So therefore, we integrate over V, because then this Laplacian and the integration commute. So like here. So we can just pull out the delta H. We just can pull it out from the integral. And here on the right-hand side, you will say, wow, but that depends on V. No, it doesn't, because it's an invariant trace. So capital K squared, I can replace with lowercase k squared, because it only depends on the eigenvalues of capital K. So also on the right-hand side, I can interchange this term with the integration. Now you see, I have now a new matrix plane wave equation, but for the matrix plane wave averaged over one of the diagonalizing groups. Now I use once more the invariance of the harm measure, as I just explained it. Now, because the notation is swapped now, because we go via the matrix plane waves, I use it in the form that I use the invariance of the harm measure of V. So I absorb the U in that case. But of course, it doesn't make a difference. It's just a matter of choice. So this integral here, d mu of V, e to the I trace hk, I just insert now its diagonalizations. I integrate over V. I use the invariance of the harm measure, and I see, whoa, the U is completely gone. I have removed the U. And then I arrive at this canonical expression, and that is a so-called spherical function, and it's named after Gelfand, who was actually the first to write it down or to emphasize it in that form. Spherical functions are generalizations of Bessel functions. So this is, as I show you in a minute, a generalization of the Bessel function J0 that you know. I do not want to give a fully fledged definition of spherical functions. I just want to say one important feature of them is, first of all, a symmetry between x and k. So I can obviously interchange x and k. And if I put either x to 0 or k to 0, I get 1. Because I can normalize the harm measure to 1, or to the group volume, whatever you like. The point is, this thing, even so, we started from the matrix plane wave containing fully occupied Cartesian matrices H and K. It only depends on the radial variables, on the symmetric spaces, on the eigenvalues, due to the invariance of the harm measure. It's very important. But this means now that this Laplacian, Cartesian Laplacian, which contains degrees of freedom of the eigenvalues of H and also of the angles of the U in H, that acts on a function which only depends on x and k. It does not depend on U anymore. So I can replace this delta H by its radial part. What is a radial part? Well, in the case of vectors, if you have the Laplacian in 3 dimensions, or let's begin with 2 dimensions. Laplacian in 2 dimensions, what the radial part is. 1 over rho, d rho, rho, d rho. In 3 dimensions, it is 1 over rho squared, d rho, rho squared, d rho. So we need a generalization of that. And here you see, the radial equation now is the following. It's only the radial part of the Laplacian acting on the matrix Bessel function, on the Gelfand spherical function, and you have minus trace k squared, and again the Gelfand spherical function. And this is a radial Laplacian. And you see, it just generalizes what you know from vector spaces. In vector spaces, we have only one radial coordinate. But what enters expressions like 1 over rho, dd rho, dd rho, or 1 over rho squared, dd rho squared, dd rho, is simply the radial part of the Jacobian. And this is the same here. And what is the Jacobian? The Jacobian is a Vandermonde determinant lifted to the power beta, absolute value square of it. So it's a very, very natural generalization what you hear. The sum over all eigenvalues, Jacobian inverse ddxn, Jacobian ddxn, d after by ddxn. And again, here's a Vandermonde determinant. Now, as in the case of the radial operator, I can rewrite it in other forms. I mean, you know that. I can write it in forms like d squared, rho squared plus 1 over rho dd rho, or in 3 dimensions, d squared d rho squared plus 2 over rho d rho, and so on. And the same we can do here. So equivalent formulation of the radial Laplacian is this here. So that completely corresponds to that. So we have here a flat Laplacian in the eigenvalue space, and here something which contains a lot of curvatures and first order derivatives, and you see it goes with beta. You see that beta plays here a role very similar to the dimension in the case of the vector Bessel function. So if we are in 2 dimensions, 3 dimensions, 4 dimensions, or so on. But this is natural, because beta told us what was the underlying number space over which we defined our matrices. So we have a matrix generalization of the Bessel operator, and let me once more reiterate, I could have written all that also in terms of the eigenvalues of k. So we have a full symmetry of this Gelfand spherical function or matrix Bessel function in x and k. I want to emphasize that because in a few minutes I will briefly speak about Jack polynomials and such things, and they are not symmetric. So this is one of those misunderstandings quite often, that people think that these functions are just Jack polynomials. They are not. They are really not. Sorry, just 1 second. So, sorry. I'm back now. So, yeah, and here comes now a comparison. So if I have in the vector case, so in 2 dimensions, a vector k and a vector r and a vector angle cosine phi between them, this is my Bessel function in 2 dimensions. So z is just the product of the length of k times the length of r, and I have to integrate over the angle between them. That's cosine phi, and that is a horrendously complicated expression. You know that. That's a Bessel function case. And you also see it's spherical in the sense in which I define. So if z is 0, it is 1. In 3 dimensions, it looks very different, because in that case, I have to use another integration measure. Here I have to use a full solid angle. So I get a sine theta, d phi, and I can choose my coordinates in such a way that the angle between k and r is theta. So it's cosine theta. And then you see this looks more complicated, but it's a much easier function. It is just sine z over z. And similar things appear now, but in a much richer phenomenology for these Bessel functions in n by n matrix spaces. And as here, it's strongly, so if we can do that or not, strongly depends on beta, which is a dimension of the underlying space. So is it a 2-component vector, 3-component vector, or here are these matrices built on real numbers, complex numbers, or quaternions. All that what I just told you is directly linked to exactly solvable systems. So let's make an ansatz. So I write my matrix Bessel function in terms of a new function theta, also depending on x and k, and I want to make this answer symmetric. So I divide by beta, by the beta over 2's power of the product delta n of x, delta n of k. So these are the Vandermonde determinants. Please notice that there are no absolute values here. With some algebra, which is nasty but doable, no problem, I can derive from that an equation for this function theta. And this has this form. It's again an eigenvalue equation, so an operator Lx acting on this theta gives trace k squared times the theta. And now the question is, what is this operator Lx? Well, it is indeed a Hamilton or Schrödinger operator. So physicists call it a Hamilton operator, mathematicians for some reason call it a Schrödinger operator. Why? Because this here is a kinetic energy part in a flat space, in a flat n-dimensional space spanned by these x's here. And now here I have a potential part. I have a second order interaction, 1 over xn minus xm squared, sum over all the differences. And the really interesting part is that this interaction is scaled here with a factor beta times beta minus 2 divided by 2. Well, first of all, you see, I can now play with the beta. So what do I get for beta equal 1? I get 1 times 1 minus 2, which is minus 1. So I get minus 1/2 times this expression. What do I get for beta equal 2? I get 2 times, 2 minus 2, so that's 0. I get nothing. So that is like a free, so these are free particles. These are end-free particles. What happens for beta equal 4? I get 4 times 4 minus 2, which is 2, divided by 2. Okay. In any case, I get something positive here. So 4 times 2 divided by 2 is 4. So that was positive. So I see, depending on beta, I have a repulsive case, I have a free case, and I have an attractive case. And mathematicians, but also people in statistical mechanics are very interested in these models. And these are models of the Kalot-Geo-Sutherland type. Now comes a surprise. Nobody can say it's illegal to choose any type of beta, any type of continuous parameter. So this is a well-defined model. This is a well-defined abstract many-particle model for any type of beta. Remember, we started from groups. So beta 1, 2, 4 were classical group cases, orthogonal, unitary, and symplectic. And now we see on this level, we don't have to make this restriction. And people are thinking about that a lot, really a lot, because people try to find sort of more general structures than the Lie groups in which they find as special cases these beta equal 1, 2, 4. That has to do with quantum groups and with other generalizations. So it's a very, very, very interesting mathematical field. Now, solutions of these equations are given by the Jack polynomials. Well, personally, I don't like the Jack polynomials very much. I tell you what one does. I take this integral here, and first I expand the exponential function. Then I see, I have to integrate, I have to do averages over the group, over traces u to the minus 1, x u k to all kinds of powers, to infinitely many powers. This I can actually do, at least for the unitary case, I can do it quite well, with the theory of Young tableaus and so with some advanced group theory. Any case, what you get is very, very complicated. So the Jack polynomials are very popular objects in pure mathematics, but they are very, very complicated. But importantly, they are not symmetric. So the way how people define them and use them, they are not symmetric anymore in x and k, because the k here for them has a meaning as an eigenvalue in this form. So they don't want them to be symmetric. So put differently, our Gelfand spherical functions, or these matrix Bessel functions, are like envelope solutions for these Jack polynomials. Okay, but the really tricky feature was that for beta equal 2, this interaction part vanishes, so I have something trivial. I have a trivial flat Laplacian for n particles in n dimensions. Sorry, I just see that I disappeared here. So here I'm back again, sorry. And therefore, this case is special. Itzigson and Zuber, they observed in the 80s, or actually 1980, they observed that by this very feature, I can solve this exactly solvable particle type of problem. So I can solve this equation. And what I get is actually e to the I x n k m's. And due to symmetry, all exchanges that you have. And because I used here, to get this function theta, I used here beta divided by 2. For beta equal 2, that's just 1. I have to just remultiply this expression again with that. So you see already from what I told you that this is really the solution, the exact solution of the Gelfand spherical function for beta equals 2 and arbitrary dimension. And this is amazing. And people were really excited at the time. And it is one of the most beautiful results in statistical mechanics. And it has been used a lot, really, really, really a lot. And from the point of view of exactly solvable systems, this is so because the unitary case corresponds to an interaction-free case. Now, you can imagine that all other cases, different from beta equal 2, must be extremely complicated. Unfortunately, it is so. I do not want to now present you results on that because that would be really, really messy. So let's just stick here with that case. And now a surprise came. So Itzigson and Zuber, they found that in 1980, and they were very surprised to hear that it's actually a special case of a much older result due to Harish-Chandra. Harish-Chandra presented this mathematical result here in 1957. If G is a compact semi-simple Lie group, A and B are fixed elements in the Cartan subalgebra H0 of G, then this integral, which looks very, very, very much like the Gelfand spherical function, the Itzigson-Zuber integral, can be exactly written in this form. We have again here an exponential factor. W is an element in the Weil group. So I sum here over all elements in the Weil group, and the P's here are the root systems. If you don't know what that is, just it is not very complicated actually but for those of you who are a bit more familiar with group theory, I just wanted to present this result. Also, if you don't know what it is, if you're not familiar with group theory, we won't need it in the sequel. There's a question? Pardon me? What? The slides are now? Oh, but they move here. Okay, I kill it and restart it, yeah? No, thank you for telling. Is it back? Now, yeah. So if you are familiar with group theory, I just want to present you that as a classical result. If not, we won't need it afterwards. But I just want to make the connection for those of you who know this part of group theory. So an integral, which looks very, very much like the Itzigson-Zuber integral, in case that G is a compact semi-simple Lie group and B are fixed elements in the Cartan subalgebra of this group, I can do explicitly, or Harish-Chandra did it explicitly, in this form as a sum over the elements of the Weil reflection group. And so the pi's are the root systems, and so on and so on. And now you will ask, whoa, that generalizes the Itzigson-Zuber integral also for beta equal 1 and beta equal 2. Unfortunately, not. And this is a point I really want to make for those of you who are interested in group theory and such things. Because these integrals have the restriction that A and B are fixed elements in the Cartan subalgebra, while the Itzigson-Zuber or Gelfand spherical functions they, in that cases, the diagonal matrices X and K are not in the Cartan subalgebra. They are supposed to be in the radial space of the symmetric space. So these are the eigenvalues. And only in the unitary case, because U of n divided by 1, the Hermitian matrices are equivalent to the unitary one, these two spaces coincide. So therefore, even though this is a powerful, beautiful result, it only relates to the Gelfand-Zwerkel function or the Ising-Super integral in the case beta equal 2. Okay, but this is already a lot. There is a famous, or there are two famous papers by Mehta and Pandey in the early 80s, application to time reversal invariance breaking of this Ising-Super integral. So GUE and GSE preserve time reversal invariance, and therefore there are two models for time reversal invariance breaking, the GOE-GUE transition. So here we go from H1 to alpha H2, and the GSE-GUE transition where we start from Gaussian symplectic ensemble and go to unitary ensemble. And using the Ising-Super integral, these authors could express all the PDFs in terms of the eigenvalues of H of A, so as a PDF. And therefore, even better, they could do these integrals over the eigenvalues of H of alpha and write them in Pfaffian or quaternion determinants for arbitrary K-level correlation. So it's a very, very beautiful paper. So two very beautiful papers. Okay, yeah. I come back to this point, but in the context of supersymmetry. So now I want to speak about supermathematics. So when I give such talks to friends or colleagues in mathematics, they always laugh when I present transparently speaking about supermathematics. They always say, well, mathematics by itself is already super, so why do you want to have supermathematics? Well, but this is a name that people use. So, I mean, take it seriously or don't take it seriously, but this is just a label or a name. The idea is the following. We have a set of K1 complex commuting variables, set P running from 1 to K1, and these are just ordinary complex commuting variables. And now we formally introduce K2 complex anti-commuting variables, and we call them zeta. Throughout, I will try as much as possible to use Latin letters for the commuting variables and Greek letters for the anti-commuting ones. Anti-commuting simply means that. You know that from fermions or from vector products or things like that. Zeta P times zeta Q is minus zeta Q times zeta P. So they anti-commute. Well, but if I take here Q equal to P, I see that zeta P squared equals minus zeta P squared. So zeta P squared must be 0. That's an interesting feature. But that means that's the most general function that I can write down of, say, two anti-commuting variables, zeta 1 and zeta 2, is this. This is the most general function because there are only terms to order 0 and terms to order 1. So I have a constant C0, I have another constant times zeta 1, another constant times zeta 2, another constant times the product of zeta 1 and zeta, and that's it. You cannot construct other terms containing zeta 1 and zeta 2, which is non-zero. You cannot. Okay. Let's make a bit more, bit richer, because we started here with complex commuting variables and that complex anti-commuting variables. So what is a complex conjugation? Well, we formally associate to every variable zeta p a variable zeta p star. And if we double star it, so if we want to go back to zeta p, we make the agreement that we get a minus sign. You might find that a bit counterintuitive. Well, there are two ways of trying to consistently handling these minus signs which appear here, and this is one way of doing it. But I guarantee this definition is consistent. It might look a bit weird right now, but it's a consistent definition of a complex conjugating twice. Importantly, anti-commuting variable also anti-commutes with a complex conjugate of an anti-commuting variable. And again, importantly, commuting and anti-commuting variables always commute. This is also very important. Okay, now we have already some structure. Needless to say that there is no way of representing an anti-commuting variable as a number. So commuting variable, you can say complex commuting variable. Okay, it is 4 plus I times 3.2 or so. But there is no way of doing something like that for an anti-commuting variable. These are just formal objects. But in a few minutes, you will see why they are extremely useful formal objects. Here I want to show you one of the examples that demonstrate that these anti-commuting variables are like a beautiful playground for people who like mathematics. I want to give you now a list of weird identities which appear due to the anti-commutation property. Functions such as exponential function or cosine or whatever involving anti-commuting variables can only be interpreted as power series. Same with matrices. If I have a time evolution operator, or with operators, if I have e to the I a matrix, this means that it's a power series. Now, but as I just demonstrated, the square of an anti-commuting variable is 0. These power series must terminate. And once more, so each of these functions, whatever you choose, is a finite polynomial. So let's look at some examples. So let's look at the exponential function of zeta p star times zeta p. Well, I expand it as a Taylor series and I get this here. All higher order terms are 0. But this is the same as expanding this here, 1 over 1 minus zeta p star times zeta p in a Taylor series. It's the same. Yeah, but I could also expand square root of 1 plus 2 times zeta p star times zeta p, and again I get the same. Or I could say I take 1 plus the sinus of zeta p star zeta p. I get again the same. And I could take logarithm 1 plus zeta p star zeta p, and again I get the same. Here please notice that zeta p star times zeta p is commuting. So the product of two anti-commuting variables is commuting. How can I see that? If I have zeta p star and zeta p, and now I come, say, from the right with another anti-commuting variables, let's say zeta q, and I want to exchange it with zeta p, I get a minus sign. But now I also want to exchange it with zeta p star, and I get another minus sign. So you see, that commutes. So it's commuting. And if I come now with some real numbers, zq, it obviously also commutes with that. So this product is a commuting object. That's also important. Now, we need some linear algebra. So there are two ways of defining supervectors. The most handy one, the most convenient one is if I order a supervector in such a way that I have my k1 component vector z of the commuting complex variables here on top, and the vector k2 of anti-commuting with dimension k2 of the anti-commuting here in the bottom part. I could also do it the other way around, but it turns out that is actually for what we're doing the most convenient part. What would be a supermatrix? Now, again, different choices, but the one that makes mathematically the most sense and leads to consistent expressions is the following. I have on the diagonal blocks, I have matrices A and B. These are matrices which have commuting entries. That does not mean that the matrices commute. They only have commuting entries. And on the off-diagonal blocks, I have matrices with anti-commuting entries. By the way, K1 and K2 can be different. In that case, A would be a K1 times K1 matrix, so a square matrix, and B would be a K2 square matrix. But mu and nu would be rectangular, K1 times K2, respectively K2 times K1 matrices. Now let's see what happens if I let such a supermatrix X on a supervector. So I have here my supermatrix and here my supervector. I let it X, and I just do it in the usual way. So I get here A times Z plus mu times zeta, and here nu times Z plus B times zeta. And now I see, A times that is certainly a commuting structure. But mu times theta, that is also a commuting structure, because I have always products of two anti-commuting variables, and that is commuting again. Okay, so I can call that Z prime. It's a vector of commuting variables. And here I have mu times Z, so I have anti-commuting times commuting. This is definitely anti-commuting. And here I have B times theta, so that is something commuting times anti-commuting. That's again anti-commuting, so I call this Z prime. So I get indeed a supervector of the same form. So this linear map, using these supermatrices, reproduces vectors of the same form. So I stay within the same spaces. Okay, now we need also invariances. So we define a supertrace in such a way that it allows for cyclic permutation. So supertrace, supermatrix sigma 1 times sigma 2 should be equal supertrace sigma 2 times sigma 1. And it is amazing that the simple definition of the supertrace equal to trace of A minus trace of B does the job. So if I define the supertrace in this simple way, I indeed have this property. Check it out. It's a short calculation. Similarly, we want to have a superdeterminant in such a way that the superdeterminant of a product of supermatrices is a product of superdeterminants of these matrices. And again, the definition is not very complicated. If you know a bit about Schur decomposition and so on, it won't surprise you. But if not, then I can try it out. If I define the superdeterminant of sigma in such a way that I say determinant of A minus mu times the inverse of B, which of course has to exist, times nu divided by the determinant of B, and this has exactly this property. Now we have some linear algebra, and we even have some matrix invariance. Now we need some analysis. So first of all, we should define a derivative. Derivative with variables which do not have a representation as numbers? How could that be? I mean, derivative in ordinary spaces is some, epsilon, delta, and so on. Okay, here we have to define it in a different way as a discrete operation. So the derivative of Zp with respect to Zq is meant to be the Kronecker delta of the two. Importantly, the derivative of a complex conjugate with respect to a not complex conjugate is always zero. That is just a definition. Of course, this has no bearing on what you know from ordinary analysis. Similar to the integrals, this has nothing to do with the Riemannian or Stieltjes integral or whatever. It's just a definition. We define that the integral over an anti-commuting variable is zero, and an integral over 1 of an anti-commuting variable is 0, and the integral over the anti-commuting variable is 1 over some constant, 1 over square root of 2 pi. Now you probably ask the question, what is that good for? Why do we want that? Well, because as you will see, these definitions work beautifully with what you know from ordinary analysis. Amazingly, they work together so beautiful, as if they had been good friends for thousands of years. So, I mean, the Bayesian integral, even though it's something very, very different from the Riemannian integral, works nicely with the Riemannian integral. I'll show you in a minute. So, for example, I want to integrate e to the minus a theta p star theta p over theta p star and theta p. As we already learned, I can expand the exponential functions only this term, and using all these rules, I get a over 2 pi. But if I had applied this rule of taking derivatives, you see, I would have gotten exactly the same, apart from this factor of 2 pi. So the amazing property of these definitions is that apart from some numerical factors, derivative and integral are actually the same. This is, by the way, the reason why mathematicians do not very often work with the Bayesian integral. They like to think of all that as one derivation. So they are not really fond of having two different notions for the same thing. They say it is a derivation. So why does it work so well together with the Riemannian integral? This you see if we make a change of variables. So we have some supervector over which we integrate, and now we want to integrate over a new supervector chi, which is a function of the old one. So we have to generalize the notion of a Jacobian, and that is called the Berezinian. And you see, it is just what you would naturally assume. So this integral is given as this integral, in which here, instead of the determinant of the derivatives, is just the superdeterminant of the derivative. So this contains, it includes the old change of variables rule for n-dimensional integrals. It's something very beautiful. So, and this should sort of intuitively make clear how well these two, the Riemannian integral and the Berezinian integral, work together. Okay, now we have to come a bit closer to random matrix theory. Good, let's do that. So actually, what is the time? I have 1 hour more, right? Half an hour more. That's what I mean. Okay, fine, good. That's very good. That's very good. Thank you. Was a bit confused. Yeah, let's come a bit closer to random matrices. Let's look at the following. We look at an ordinary matrix with commuting entries. Let's call it A. We look at our vector again with commuting entries, a set, and you could call it bosons if you wish, but that's only a name because we're not talking about physical particles here. But people do that. People call that boson and fermions for the vector Z, which has anti-commuting entries. Now, in that case, we choose K1 equal to K2 equal to K. So A is a K by K matrix, and Z and zeta are K-dimensional vectors. Now, you know that this integral over the complex commuting over the vector with complex commuting entries of this matrix, the Fresnel type integral gives the inverse of the determinant of A. And generalizing this here, it is actually easy to see that the integral over a vector of anti-commuting variables of the same determinant gives the determinant, not the inverse of the determinant, just the determinant. Isn't that amazing? So if I multiply these two expressions, the right-hand side is not dependent on A anymore. And this actually was historically the reason, or the major reason, why Wess and Sumino introduced supersymmetry in particle physics. Because by doing something like this, so by assuming that each boson has a fermionic partner and each fermion has a bosonic partner, certain divergencies, so certain free normalization problems just disappeared. But let me reiterate, we have no connections to bosons and fermions here. We're using the same mathematics, but in a completely different context. So I'm not talking about supersymmetry in the sense of particle physics. I'm only talking about supersymmetry in the sense of statistical mechanics. Good. Now, if sigma is a supermatrix and psi is a supervector, then this integral here gives the superdeterminant to the power minus 1. We will need all three integrals in a minute. Because now we want to apply all that to random matrix theory. Yeah, I gave you the definition of the correlation functions as mathematicians do it. So I said, okay, for an n by n matrix, we have a joint PDF of the n eigenvalues. And to calculate the PDF of having an eigenvalue in each of the infinitesimal intervals from energy to energy plus differential of this energy, I just have to integrate out n minus k of the n variables because I want to do that regardless of labeling. Physicists prefer other definitions. Physicists like to work with resolvents, and therefore the physics definition of the correlation function is slightly different. Here, I average over my Gaussian random matrices over an ensemble. Actually, I write these formulas always for beta equal 2, but with obvious generalizations, they would also be true for beta equal 1 and beta equal 4. And this is now a product of the traces of the resolvents. How can I see that this is very related. It's actually not exactly the same as the mathematical definition. But first of all, this is an invariant definition. So it depends only on the eigenvalues of H. So I could as well write 1 over xp plus minus E, E being the diagonalizing matrix of the eigenvalues. And then the trace is just the sum over 1 divided by xp minus En. And then I have this plus minus here. And that, you know, there is this beautiful formula that tells you 1 over x plus minus En equals the principal value minus plus IP times the delta function. Aha, so we have delta functions here. So we integrate out k, if we have k-fold product of that, we always integrate out k of these integrals trivially as delta functions. Aha, which means this relates then to the mathematics definition because I'm here in this integral left with then n minus k integrals. Now you will say, wow, but there is also this principal value part. Yes, this is also there, so the Cauchy principal value, and we can always deal with that. So we can subtract it or keep it as we wish. So these functions are a bit more general than the mathematics definition. But I mean, they are fully equivalent. So that is what I want to say. Now, to introduce supersymmetry, we first have to write these functions as derivatives of a generating function. This generating function I call Z. And we need to introduce source variables. These source variables are called J. I have K of them. So I now want to introduce a generating function in such a way that the k-fold derivative with respect to each of these source variables at j equals 0 reproduces precisely these functions. And you can easily check, this is really one of those exercises you can do, that this is the right generating function. So we have an ensemble average of a product of ratios of determinant. So if h minus xp, you might want to add the plus minus if you wish, minus jp, and here we have the same expression, plus jp. Yeah? So I leave it to you as an exercise that indeed, doing the derivative with respect to the jp's, you get these traces. Yeah? So this is really, take the derivative, you get these traces. But only if you have a ratio of these two determinants. If you take only one of them, you won't get that. You need a ratio of these two determinants. And this is very important. It's very, very important that you get the correct normalization of this generating function and rid of terms involving determinants which you do not want to reproduce this expression here, only if you have a ratio of these determinants. Otherwise not. But now you remember that we just spoke about Gaussian integrals, which produce determinants and 1 over determinants. And this is exactly what you see here, determinant and 1 over determinant. So we do the following. We write this ratio of determinants as an integral over complex commuting variables. So this is a this is a vector of complex commuting variables. This is a vector of complex anti-commuting variables. And here I have my e to the I something term, as you have seen it on the previous transparencies, involving, in that case, here what is in the denominator, and here what is in the numerator. Why is that so fantastic? Well, because we want to do this ensemble average over the H. But if we have it in this form, this ensemble average becomes very easy. Because I can view ZP dagger H times ZP, this quadratic form, as a trace of H times ZP dagger. I can just by cyclic invariance under the trace. Same here, but because these are anti-commuting variables, I get a minus sign. Because collecting everything that what depends on H gives me this expression here, and if you look at it, you see this is nothing else but a Fourier transform in matrix space of my Gaussian probability density. I can do that. I can trivially do that. And then I'm left with e to the minus trace of this sum here involving all these vectors zeta p, zp, and zeta p squared. And now comes a miracle. I can reorder this expression in a very handy way as a supermatrix B and I have to square it. And this is a form of the supermatrix. The supermatrix contains all possible scalar products in block form. So it's a block matrix constructed in this way. Here I have the scalar product of the commuting vectors, scalar product of the vectors with the anti-commuting entries, and here's the mixed ones. Aha. But this is a supermatrix. It's actually a well-defined supermatrix. So I can use a supermatrix of the same symmetry and do another Fourier transform. So why would I do that? Why? Because I have here drastically reduced the number of degrees of freedom. So if you count, the dimension of this matrix B is not n, as it was here in the case of the matrix H. It is 2k times 2k for beta equal 2 and 4k times 4k for beta equals 1 and 4. So k being the order of the correlation function you want to consider. Aha. Okay, now I use my Fourier transform in superspace to linearize this B again. And then I see I can rewrite this linearized expression with my new supermatrix sigma in this form. Yeah, and then I have again Fresnel type of integral over my supervectors, which I can do. And then this is now the collection of the results. This is what we started out from, generating function. This was my generating function here, with the ratio of determinants. And this is now my superversion. So this is an identity. So these two expressions are really identities. What is the difference? Here I have the generating function as an integral over an n by n matrix. And at the end of the day, I want to do n to infinity. Here I have an integral over supermatrices of a dimension which is proportional to k. And what I have here is that n is an explicit parameter. So this really makes life a lot easier. So I have a drastic reduction of the dimension, and my n is an explicit parameter. Now, shortly, want to say something about the groups in superspace. Of course, we also have to diagonalize our supermatrices. We have eigenvalues. People call them bosonic and fermionic eigenvalues, which is a really stupid jargon because they are not commuting or anti-commuting. These are just always commuting entries, these eigenvalues. So there's nothing commuting or anti-commuting about them. So the diagonalizing supermatrices U, however, they have commuting and anti-commuting entries. They are elements of supergroups which contain the ordinary groups. So in the case of the unitary ensemble, it's a unitary supergroup in K1 bosonic, K2 fermionic dimensions, which includes the direct product of the ordinary Lie groups in K1 and K2 dimensions, unitary ones. Oh, sorry, that should be one index K1 plus K2, not a 1 times K plus. Now for the GOE and GSE, we have another group structure, and that is the unitary orthosymplectic supergroup. So it comprises features of all three, of the unitary, the orthogonal, and symplectic. And so it has to require two conditions. First of all, U dagger U has to be the unit matrix, so that is just like here. And then it has to satisfy a second condition, so that's a transpose of U times the matrix M times the matrix U is M again, and M has this form. And here you see, aha, that is unitary part, and orthogonal unitary or orthogonal part. And this here is typical for symplectic matrices. So the unitary orthogonal symplectic group contains the direct product of the orthogonal group in K1 dimension and of a unitary symplectic group in 2K2 dimensions. Which means these were my matrix spaces, so the real symmetric Hermitian and Hermitian self-dual ones. So the corresponding symmetric superspaces are UK1, K2 by 1 for beta equal 2, and then GL, so the general linear group, K1, 2K2 divided by OSP, K1, 2K2 for beta equal 1 and 4. The point is there are two forms of doing this here, of doing this quotient. And one form belongs to the beta equal 1 and the other one to the beta equal 4. So this explains on a very deep group theoretical level why the orthogonal and symplectic cases have certain things in common. And once more, as in the ordinary case, Symmetric spaces have an angular or group part and a radial or eigenvalue part. That is the same in ordinary space and in superspace. Yeah, and then there are also generalizations of the Ising-Zubair integral, for example. So if I integrate over the unitary supergroup, this form here, just generalizing what you have seen for the Ising-Zubair integral, you get a straightforward generalization of the Ising-Zubair integral. Here you get a Jacobian of this form. So it has van der Mondes here for the bosonic and fermionic eigenvalues, and then products of all the differences. And for K1 equals K2 equals K, the case that interests us actually, this can be written due to Cauchy's lemma in terms of a determinant, K by K determinant over 1 over the differences of the bosonic and fermionic eigenvalues. However, if I choose K1 and K2 equal to n and 0 or 0 and n, I get my Ising-Zubair integral back. Now, how can we apply that to random matrix models? Well, first of all, I want to, adding to what I just said about these Ising-Zubair integrals, show you exact solutions of the random matrix problem. However, here I have to say that only works for beta equal 2. So I speak only now about transitions to the Gaussian unitary ensemble. So this is what we started out from. And then in superspace, we have this generating function here. Integral over a 2k times 2k Hermitian supermatrix. And here you see it is over a superdeterminant involving a direct product of the n by n unit matrix in ordinary space and the supermatrix. And here's the H0, which I, of course, cannot transform in general into superspace. So it's an n by n matrix. And here a unit operator in superspace. So I have direct products between ordinary and superspace. But I have also this form here involving the sigma, the arguments, so the energy arguments and the source variables, and I can do that with the Ising-Zubair integral. And if I do that, I get here this form. All angles are gone. And this form I can immediately write as a determinant, or as a k by k determinant of a kernel. And I get this function bk, which I have introduced here as this k by k determinant ratio in front of it. So this is what you have seen here. This is the fastest way of deriving a result which in mathematics people worked a lot on these things. This is by far the fastest way of deriving that even for these transition ensembles, correlation functions have a determinant structure. So when people speak about determinant processes, so everything what you need to know about determinant process you have seen on the last 2 or 3 transparencies. So the kernel you can write as a double integral in this form, and there are also much more complicated ways of deriving it. And if you want to see the original way of deriving it, it was actually the supersymmetry. You see it here in an old paper by myself. So can we use that for something practical? Okay, let's do it the transition of a regular ensemble to a Gaussian unitary ensemble. And let's look at the 2-level correlation function. I showed you this picture already the day before yesterday, but now you know how it was derived. It was derived with supersymmetry. For alpha equals 0 in the regular case, I know that the 2-point correlation function is just a constant 1. So there's no level repulsion. But if I now switch on with my transition parameter alpha over d, d being the mean level spacing, a tiny little mixture of the unitary random matrices, I lift all degeneracies, so the probability density drops to 0. This correlation function, there's some overshoot here. I make the lambda larger. I slowly, or relatively fast actually, I evolve into the limit for the Gaussian unitary ensemble. This is on a relatively short spectral scale. If I go to huge spectral scales, of course, I have this bending away from the logarithmic result to the linear result as much larger scales. Put differently, this transition is very fast on shorter scales, but on very large scales, of course, you will always see it somewhere. Yeah, now I want to emphasize something. Let's consider the case beta equal 2. So we have 2 ways of looking at that. We have one way of looking at that in the ordinary symmetric spaces. So we have Hermitian n by n ordinary matrices, and we diagonalize them, U deca x U, U an ordinary unitary n by n matrix. And that is now my volume element. I have here the van der Monde determinant squared. Here I do not use the absolute value sign because I have the square. I have here the product of the eigenvalues, and I have here the Haar measure. I see immediately the level repulsion because I have here the van der Monde determinant with the product of all differences. Now I map it to superspace, and then I have Hermitian 2k times 2k supermatrices of this form. And again, I have some unitary matrix diagonalizing them, and S are the eigenvalues, so the bosonic and the fermionic parts of the eigenvalues. Change of variables implies something very similar to this. I have a Beresinian here, which gives me, instead of the van der Monde determinant, this function here, which is the square of this function, which we have already seen many times now, which is the square of a k by k determinant involving all inverse differences of bosonic and fermionic eigenvalues. And I get the Haar measure of the unitary supergroups. So here I see the level repulsion, so in ordinary space. But in superspace, I see immediately the determinant structure of the k-level correlation functions. I see that immediately. So something which is very difficult to find for transition ensembles, in ordinary space, you see immediately, it is sort of a built-in feature of supersymmetry, even for transition ensembles. Yeah, so this was now for the unitary case. But actually, the beauty of the supersymmetry, let me go back to this here one. The real beauty lies in the fact that, that the n, so the original matrix dimension, is an explicit parameter here, it's a large parameter. So therefore here, we have to do the integrals first, and then we can do the limit n to infinity. But here we can first do the limit n to infinity by some mathematical tricks like steepest descent, saddle point approximation, all kinds of things. Okay, and this I want to tell you now how that works. And that is even more general than what I just told you about this Itzinger integral. So this works for all beta. So here's once more my generating function. Here's the n minus n as an explicit parameter. Let us write this in terms of a free energy, L of sigma, minus L of sigma. I use that the determinant is e to the trace of the logarithm, and this carries over to superspace. So I have here, this free energy is supertrace of sigma squared plus n times logarithm of sigma minus x minus j. You see, I absorbed here in this minus sign, and this minus sign. Now, the j, the source variables, I can make infinitesimally small. So actually now to determine the saddle points of these integrals, I don't have to consider them. I can put them to 0. So let's put the j to 0. And then I determine saddle points of this free energy in this matrix space by just varying the L with respect to the sigma. So I calculate dl with respect to sigma. Now, due to the super trace here, I get invariant expressions. So I see that these equations which I get now are not matrix equations anymore due to the super trace. I just get one equation for all the eigenvalues. And this is the equation, 2 times S0. S0 is now the variable standing for all the eigenvalues at the saddle points of sigma, plus n divided by 0, S0 minus x. This is an easy equation to solve. This is a solution. X plus minus I square root of 2n minus x squared divided by 2. Whoa! If I take the imaginary part, this is Wigner's semicircle. Do you remember that? Wigner's semicircle was a asymptotic, so the large n result of the level density. Aha, now we understand what the saddle points describe in the supersymmetric formulation. They describe the smooth part related to the level density. So if we now want to integrate around these stable points, so around the saddle points, so we are sort of already in the perfect coordinates. Yeah? We explore now the fluctuations around the level densities. So I do not want to do that in detail because it's very, very technical, mathematical, and so I just want to describe it in words. So the integrals corresponding to the level density. So the integrals just sort of linearly leading away from the Wigner semicircle. There's just boring Gaussian integrals. In a field theoretical context, I would call them massive, but this is only a name because there are no masses here. So remaining integrals, they are related to the group structure of sigma. They explore the surrounding spaces, and the correlation functions result from the corresponding integral over the so-called massless Goldstone modes. So if you are a bit familiar with field theory, these are really Goldstone modes now. And massless is again just a word because there are no masses here. Which means I have to introduce super matrices Q, which live in a reduced space, in a subspace resulting from the subtle point approximation. So for beta equal 2, and for the 2-point function, it is actually this space, U1, 1, in the bosonic dimensions, 2 in the fermionic dimensions, divided by U1/1 and U1/1. So I have to divide that out. So that is a coset space. Now you will ask, we never spoke about a comma here. We had previously something like U2/2, and now we have U1, 1. This is so because in doing by this subtle point approximation, doing the random matrix problem forces us to put the imaginary increments on different sides of the real axis, and that introduces non-compact degrees of freedom. But because we do not want to work explicitly with that, this is not so important here in that context, more important, even though it's terribly important, for, of course, if you want to do it. But here for the group theoretical part, the structure is a coset manifold. And for beta equal 1 and beta equal 4, it is this coset manifold of the USP2, 4 divided by USP2/2 USP2/2. And this is a very, very widely applicable. The standard example, and that is actually where it came from, in a beautiful paper by Fietov, 1983, so 40 years ago, considered disordered systems. So we have electrons moving diffusively in a probe with scatterers, so with impurities. So here you see now paths of such an electrons are being scattered. And now we can ask the question, what are the localization features? I mean, you know that Anderson, who started the localization physics, posed a very important question, which is, of course, very, very meaningful for everything what has to do with charge transport, conductance, and so on. So the question we could ask is, what are the localization properties in d dimensions? So how would we model the disorder here by some random potential? So this is, the V is now the disorder potential, and that is sort of white noise correlated in this way. And now doing supersymmetry in a field theoretical setting, so more complicated than what I told you, gives us free energies of this form. Again, depending on Q is this coset space, a super trace of such an integral which comprises a kinetic part. You see derivatives here of the Q's. D is something like a diffusive constant, and here an ergodic part. Omega is some energy difference, lambda is some metric, and the Q is, again, the super matrix field in the coset space. Now, without going into any details, let me tell you that this last part, if you only take this part and you throw away that, so if you formally go to 0 dimensions, then you reproduce exactly the 2-point random matrix results. So you get exactly the 2-point correlation functions. Fietov observed that and was very surprised by that. And now if you go to 1 dimension, 2 dimension, and so on, so if you have also this part, you see, that part is now competing with the ergodic part. So the competition of these two parts, that determines the localization properties. Of course, it gets very messy and complicated, but that is the physics behind. Yeah, this I will drop because that is very, very mathematical stuff. What have we learned? The group integrals are needed to treat transitions. So this was our starting points. We got very quickly into integrals of the Ising-Zubair, Gelfand, and Harash-Chandra type. I told you that the Harash-Chandra spherical functions are different from the Gelfand spherical functions, that only in the unitary case they coincide. I also told you that Ising Zubair independently recovered the Harashkanta result for beta equal 2. Actually, Gelfand apparently didn't know it. So Harashkanta knew it, but Gelfand didn't know. I showed you that there is a very direct connection to exactly solvable systems, and this is very handy and helpful because it tells us what is really special about the unitary case. Special is that it maps these group integrals to interaction-free systems. So systems of n-free particles. And therefore, the integrals become solvable in that case. I also spoke about supermathematics and introduced the supersymmetry method. And I spoke about exact solutions in the unitary case in general, in the unitary case, and also in general about asymptotic results, so about the supersymmetric nonlinear sigma model. Don't confuse the sigma here with the symbol sigma that I use for the supermatrices. That comes from a field theory context. So that is pi and sigma in medium energy physics. Yeah, that was toughest of my lectures. So that was the mathematical physics aspects of random matrix theory, but they're as important as the practical and phenomenological aspects. Thank you very much for your attention. Questions are welcome. Jaime?
Hi, thank you for the lecture. So as you were explaining like the correlation functions in a transition, you mentioned that, well, we studied the case where both Hamiltonians were from the same group, the same ensembles, right, the GUE. And
sorry, I didn't get the last sentence. Can you repeat that?
Okay, so can you go to like slide 14? I think it would help to ask the question.
So I just find it very difficult to understand you. Is there something with the
microphone? Hear me?
microphone?
Can you hear me?
Pardon me?
Can you hear me?
I hear you, but it's
okay. So
maybe you start again. Maybe you start again.
Okay. So you were discussing the correlation functions in the transition, right? And we considered the case where both Hamiltonians came from the same ensemble. And then we like developed the mathematics. And at some point, can you go to slide 14 so I can show you where I'm thinking about?
I think there's a slight misunderstanding here. So when we talk about the transitions, maybe I should try to find this transparency.
Slide 14, he says.
Pardon me?
Slide 14.
Slide 14. Yeah, okay, yeah, but they have to look at two things. So here it is definitely not so that H upper index beta and H0 are the same symmetric space. I only want to emphasize H upper index beta has to include the symmetric space of that. So for example, H beta, if that is in the unitary, Gaussian unitary ensemble, H0 can be in the orthogonal or in the symplectic, or it could just be a diagonal matrix. Now, the confusion might come from, and that is really a bit non-trivial, that due to the invariance of the Haar measure, this group, one of the matrices, the one over I do not have necessarily to integrate, just disappears. Yeah? So the orthogonal group or the unitary symplectic group are subgroups of the unitary group. Yeah? So it can just absorb this. And because the radial space is always diagonal matrices, it is really immaterial. So when I look at these matrix Bessel functions, I can require, and I actually have to require, that they live in the same matrix space. Yeah? But still, it doesn't make a difference. It does not make a difference. Has it answered your question or not?
Yeah, that's
because look, I have here an integral. And I have here some x's, which are, say, the eigenvalues of some Hermitian matrix. And I have some k. And these k, I do not say what they are. I mean, they could be the eigenvalues of another Hermitian matrix. But they could also be the eigenvalue of the real symmetric matrix. I don't know, because I absorbed the diagonalizing group. They could also be just some numbers over which I don't average in the regular case.
Yeah. The question was on the invariance of the Haar measure. Like, I can I can shift it by whatever matrix and it can be absorbed in the metric, in the Haar measure. Because like, if you consider V being from the Gaussian unitary ensemble, I was thinking you can only make shifts from matrix which are also within the Gaussian unitary ensemble, from the unitary group, actually. So
yeah,
you can take U for both unitary, orthogonal, or symplectic. They can all be absorbed in the measure.
Let me put it in a slightly different way. If you give me radial space on a symmetric space, on the symmetric spaces I just discussed, you just give me the coordinates on the radial part of a symmetric space. I cannot tell if that is beta equal 1, beta equal 2, or beta equal 4. I need the diagonalizing group. But if I start with a unitary case as the most general one, the other two's will be absorbed in that case. Now, if I start as H upper index beta with the orthogonal case, I cannot choose for the H0 and unitary matrix. This I cannot, because I cannot absorb a diagonalizing unitary matrix in a diagonalizing orthogonal matrix. But I could simply choose the H0 in that case as a diagonal matrix, because then I would only be in the radial space. Or in this expression, which you see here, the K is anything. It could be the radial part of a unitary, it could be the radial part of an orthogonal, it could be the radial part of a symplectic symmetric space, or it could be the radial part of some regular stuff, so where I do not even have an ensemble structure.
Yeah. Okay. Yeah, understood. More questions? You want a question?
Okay, thanks for the talk. I was wondering if using the supersymmetric method, there is a clear way to see the universality of the two-point correlation function. Because when you use, for example, those words.
So I find it very difficult to say. Is there something with the microphone? I find it, I hear you, but I find it very, very difficult to understand what you say.
Can you hear me better now?
Yeah, I hear you.
Okay. So I was wondering if there is a way, like a clear way, to see from the supersymmetric method the universality of two-point correlation functions. Because if you have if you try to get the correlation functions from another method, like trying to make some word identities with the resolvent, is there a part when that is clear, the universality? So I was wondering if that universality is clear from this supersymmetric method.
I don't think I get the question. I mean, Barbara, have you understood the question? Because when you speak in the microphone, I understand you better. Okay. Your microphone seems to be better.
Okay, so imagine, for example, the two-point function of using the supersymmetric method. So one expects that it doesn't matter if we are using the Gaussian ensemble or any other invariant ensemble, the connected part of that two-point correlation function is the sinc kernel. So my question was if there is a clear way in the supersymmetric method that sinc function, sinc kernel appears clearly, without matter the ensemble of random matrices that we are using.
Yeah, I mean, yes, yeah. Okay, maybe I understand what you. When we map onto, let's see where I have this. When we use something like that here, so this expression, it looks probabilistic. I mean, here that is the first line is definitely a probabilistic statement because I have a positive definite PDF and an average over something. So this is really statistical mechanics expression. But this here is not because it contains anti-commuting variables. Formally, it looks like this. So therefore, it is very difficult to interpret the sigmas, the matrices sigma, as in a probabilistic sense. From point of view of the integrals, of just looking at the integrals, there is of course a close similarity. But I mean, you cannot extend that to a probabilistic interpretation because I really do not know how I should interpret anti-commuting variables probabilistically. Because they have no representation. I mean, they're not bound between 0 and 1, and there is no representation as number or whatever.
So that will mean that at the end we have no we have to make the full calculation in order
Yeah,
to okay.
You know, it is, I didn't want to go into that because it goes again even more mathematical. I mean, for me, this identity, which you see here on this transparency, is something like, you know, a irreducible representation. I mean, statistical mechanics lives from redundancies. So, I mean, you say that all matrix elements are treated on equal footing. So, and you take n to infinity. So this redundancy, that is always the essence of statistical models. But there are also symmetries. And supersymmetry is sort of the irreducible representation that contains all information on the redundancy, visible here in this power n, but also all the structural information. And, you know, I worked on group theory for quite some time, and this is some kind of a representation theory that one cannot really base one cannot really express in the form, if you might learn group theory, representation theory and group theory, that is some representation theory that has to be based on moments, on identities of moments. Actually, we had a joint collaborative research center with mathematicians, and I tried to explore the question with them. But the trouble was, I mean, for physicists, supersymmetry is now a well-established tool. But for mathematicians, they, you know, the thing is, there are two different ways of doing supersymmetry from a mathematics point of view. And I think they still cannot agree upon what's the right way of doing it is. So it is one of the fields where, unfortunately, the physicists are really far ahead, very far ahead in the mathematical understanding of structures, but in a non-rigorous way, of course. I mean, the mathematicians want to do that rigorously, and that is not what we do. We as physicists have always other means of checking that our results are correct by doing certain limits or looking at special cases and so on. But for the mathematicians, that's not enough. They want to do it rigorously, and they are not very far in that respect, unfortunately. So therefore, these group theoretical issues are not really, one cannot really tackle them at the point, even though I'm personally 100% sure that these are, the supersymmetry is the irreducible representation of random matrix theory.
Okay, so I think now it's getting late. Thank you again for your nice presentation.
No, thank you for listening. Thank you for listening. I hope it was not too mathematical.
So today there will be a colloquium from 2 to 3, and in the program